Okay, so I can't see the chat at the moment. Oh, there we go. Maybe if I go up there. Sorry, it's been a while since I've done online teaching now. Okay, great. Okay, perfect. Hi from the University of Edinburgh. Good morning. Hi. Okay, so a couple of things to start off with. So I've handwritten these notes. So I hope that this is going to be legible. Please let me know. Oh, that's quite all right. No, that's all we wanted, Soshan. That's fantastic. So please let me know if there's anything that you can't read. I know that my handwriting is not fantastic, but I always find it actually sort of easier to handwrite things. So yeah, just stop me at any time, and that goes both for my handwriting and for the content. If at any time you're confused, you want me to go back over something, just let me know. So the questionnaire that I sent out to you here, is that going to show up there? Doesn't seem to be updating. Okay. Sorry, I'm going to have to stop sharing again because it's not updating. We'll get there. Okay. We've got all sorts of data science problems here today. Is this showing up at the moment, or is this just a black screen?
It's just a blank screen.
Oh, no. Okay, we'll get there. I'm sorry about this. I'll stop sharing again. I did make sure all of this worked earlier, and it all seemed fine. Let's try one more time. Says that my screen share is loading. Okay, I'll talk to you while this this doesn't seem to be doing anything. So I sent out a questionnaire to all of you a few weeks ago to get an idea as to where everyone is in terms of your sort of mathematical knowledge. There we go. Okay. And that was extremely useful for me. So I asked you about various aspects of calculus, of linear algebra, of probability theory, and of sort of data science itself, things like optimization problems, decision trees, linear regression. And so it was interesting to see that actually a fair number of you have at least the basics. Some of you have the sort of intermediate, and some of you have actually seen, quite a bit already. So it's interesting that we have quite a diverse audience here. It's always great. And it also means that, the types of questions that you might have may be very different. So feel free to ask at any point. The other problem then is that I have essentially 10 hours to teach you the mathematics for data science. The question there is, where do we start and what's the best approach? I spent quite a lot of time looking for resources, and actually the best resource that I found for mathematics for data science is this book called the Mathematics for Machine Learning book, ml-book.github.io, and it's about 400 pages long. And so the question there is, how on earth do I even attempt to teach all of a 400-page book in 10 hours? The linear algebra section alone is 130 pages. The calculus is 30 pages, et cetera, et cetera. And then there's stuff on the sort of machine learning specific topics, which are about 150 pages. So we can clearly see that there's a lot to get through, but I don't want to teach everything absolutely from scratch, because I know that most of you have some experience with this. But I'm going to sort of ramp up and go through the basics relatively quickly. But again, please ask if you have any questions as we go along, and I'll be happy to stop. Okay, very good. So the route that I want us to go through is sort of to talk about concepts, and then applications, and then theory and practice. And so this should really be about what's the particular data science or machine learning application that we're interested in, and what's the theory, what's the mathematics that we're going to need in order to truly understand that. Okay, let me just see if I can see the chat. The chat has disappeared here. So as before, simply just let me know if you have any questions. You're actually going to have to just pipe up and turn on your microphones for a moment. So I don't know how far we're going to get with this. I've not taught this in this format before, but the first stuff is going to be about linear algebra. So probably today and possibly tomorrow as well, we're going to be talking about matrix representations, basics of linear algebra. And the reason we're doing this is because linear algebra is seen all over many, many different aspects of data science. But I wanted to have a particular problem to focus on. And that particular problem is what's called the singular value decomposition. So can you put your thumbs up if you have seen the singular value decomposition before? I see no thumbs up, and that is excellent news. Okay, very good. So in terms of resources that, yeah, there's a question there. Is that a question or a thumbs up? Oh,
it's supposed to be a thumbs up, but yeah.
Okay, okay, no worries, all good. Okay, so you might have seen it before. Hopefully I can still give you some novel insight into the singular value decomposition. And essentially what the singular value decomposition allows you to do is data compression and finding the important features in some data sets. One of the problems that you might have heard about in the course last week is what's called the curse of dimensionality. We're in this amazing time where we have massive amounts of data. And for a data scientist, a machine learning expert, one in some sense thinks, the more data, the better. And this is certainly true that not having enough data is a problem, but also having too much data in terms of too many features in your data sets can itself make life very, very difficult. And so what singular value decomposition and sort of a further step from that, something called principal component analysis allows you to do, is to find out which are the most important features in some data set. Okay, it might be that you've got, let's say, some data on people, and you've got height, and you've got the school they went to, and you've got their foot size, and you've got the language they speak, and you're trying to make predictions, maybe about some grade that they're going to get in an exam. Well, maybe foot size isn't very useful. And you don't want to have to go through all of your data and remove the features that you don't think are useful. Principal component analysis can do that for you. So it's a way to find which are the features which are most useful, which have most effect on some outcome variable. Okay. And then, so once we've sort of talked about singular value decomposition from the point of view of the matrix representations, we'll talk about the theory and practice behind it. Then we'll talk a little bit about calculus, vector calculus, in terms of backpropagation. So I think that last week you sort of had a lightning introduction to neural networks. Is that correct? Anybody? Did you have anything about neural networks last week, or was it just linear regression? I can't see the chat at the moment. Oh.
Yeah. Yeah, I could say we had about computers, neural networks, and machine learning, random forests. I mean, that's the gist that we, yeah.
Perfect. Okay, very good. So you probably would have seen that calculus, just taking derivatives, is pretty important when you want to do gradient descent, which is really the process which is used throughout many parts of machine learning in order to find the minimum of some loss function. Okay, which is really, you can think of the loss function as some surface in parameter space, which tells you about the difference between the actual outcome value and the predicted outcome value of some variable that you're interested in. Okay, I'm just going to close the door here because there's a massive hornet outside. Sorry. Okay, very good. And then we may talk a little bit about naive Bayes. And to do that, we'll talk about Bayes' rule, and we'll talk about inference and likelihood. Okay. And then, if there's any time, I don't know if we'll get onto these topics, a little bit about information theory and a little bit more about optimization. Okay. Are there any questions before we start? So this page looks pretty packed. Hopefully it doesn't scare you off too much, but we're going to be talking probably most of today about linear algebra. And really, linear algebra is the study of systems of linear equations. And by linear equations, we mean equations of the form some constant times, let's call it x1 plus another constant times x2 plus another constant times x3, etc., and potentially equals some other constant on the right-hand side. So this is a linear equation in the variables x1 to xn. We might call this the variables xi. And we've got some constants here. So the aij and the bi, these are just constants. And here we might have m equations. And there's something sort of immediate that we might think here, of all the equations that we could write down, linear equations seem to be the simplest. How much sort of interesting mathematical theory could there be about this? And the answer is a huge amount. So, one can take courses on linear algebra, a long way into your university degrees if you're studying mathematics, and you'll find that actually it becomes very abstract. So linear algebra itself, there's a massive amount of sort of abstraction that you can make in terms of vector spaces and all of these sorts of things, and it becomes very sort of theorem proof based when you get into it later on. Okay, but for now, we just need to think about this, that we've got a set of equations in a set of unknowns. And the question very often will be to say, okay, well, given this set of equations, what are the x's? Okay, so there are different situations that you might have. So here in these lines here, we have, two equations in two unknowns, and there are three possibilities. And in fact, there are always going to be three possibilities. Either you're going to have no solutions. So for instance, if you have the two equations, x1 plus x2 equals 3 and x1 plus x2 equals 4, there are no solutions to this. Fine. Secondly, if we have the equations x1 plus x2 equals 3 and x1 plus 2x2 equals 4, well, there is a single solution to that. That's fine. You just solve it. Replacing, for instance, the x1 variable from the first equation into the second, and you'll get an equation in x2. You solve it, and then you plug it back in, and you get x1. Okay. So you either have zero solutions, or you have one solution, or in this case, it looks like we have two equations, but actually the equations are the same. Okay, so x1 plus x2 equals 3, and 2x1 plus 2x2 equals 6. Well, those two equations are actually the same thing. And in fact, if we'd only had one equation, x1 plus x2 equals 3, there are an infinite number of solutions. That is to say that for any value of x1 you choose, there will be some value of x2 which satisfies that equation. And even though we have two equations in two unknowns, there are actually an infinite number of solutions, because really one of the equations is the other one in disguise. Had we had three equations and three unknowns, we could have had that the third equation was some linear combination of the first two equations. And in that case as well, you would find that there are an infinite number of solutions. Okay. So what we're going to do is we're going to take systems of linear equations and write the equations in some shorthand. And the reason for doing this is not only because it's convenient, but because the sort of operations that we're going to be able to do on matrices are going to make solving these sorts of systems very, very easy in general. And very often in data science, you might have some matrix with millions of entries, and you're going to want to perform operations on those million dimensional matrices. And there's a lot of libraries within Python, for instance, which can do that sort of thing very, very quickly. Okay, rather than trying to take a system of linear equations, writing it out in terms of all of these A's and X's and sort of doing some manipulation of them, there's a series of operations that one can perform on matrices, which make the whole thing much, much easier. Okay, so we can write the set of equations that we have above, the linear equations, as a simple matrix equation where we have an n by n matrix here, where we encode all of the constants, all of the A's. We have a vector here of the X's, and we have a vector here of the constants on the right-hand side. Okay, and this is simply a way of sort of packaging all of that information. Here we have an n-dimensional vector for the X and an m-dimensional vector for the B. Okay, because there are m equations and there are n unknowns. And this is an m by n matrix. And the dimensions here are going to be very important, and we're going to look at those in a lot of detail later on. Okay, are there any questions about this at the moment? I'm going to take that as no. Okay. So, of course, we need to know how to do matrix multiplication. Okay, and what we're going to do here, so the method for performing matrix multiplication seems very strange if you haven't seen it before. I know 77% of you have, and so I apologize if this is all something you're very comfortable with. But just quickly, if we want to perform matrix multiplication, what we do is we take this top row and we multiply it by the vector here. And when I say multiply it, what that really means is the dot product between the row and column. Oh gosh, it's not showing up, is it? Technology. I'm going to stop sharing and I'm going to share again. We're going to get there. Okay. So here we've got the top row of the A's multiplied by the column vector of the X's. And what we mean by that is really the dot product of the vector, of the row vector with the column vector. Okay, is this going to show up now? Yes, great. And so this top row is simply going to be a number which is going to be A11 times X1 plus A12 times X2 plus ... all the way up to A1n times Xn. Okay, and that's simply that's one entry, okay, into the vector on the right hand side. Okay, it looks like a matrix, but it's really a 1 by m dimensional vector. Okay, and the next one would be this row dotted into the vector, etc., etc. And finally, you're going to end up with the bottom row dotted into the vector. Sorry, this should be a 1 here. AM1. Okay, and we'll end up with AM1 x1 plus ... up to AMN times xn. Okay. And getting the indices right is often half the battle. Okay, so particularly when you're coding this up. So in general, as a data scientist, you would never really have to think about this all that much. You don't have to actually perform the multiplications of the matrices and the vectors together. You get a computer to do that. What's really important is that you make sure that the indices are right. Okay, so in this particular case, it's really important that the width of this matrix is n. So along here, there are n entries, and that must be the same as the height of this vector must also be n. Okay, if not, Python is going to complain. Whatever coding you're doing is going to complain. It's not going to work. So just making sure that the index structures are right is really important. Of course, you know, it's not just enough to have the index structures right. You've actually got to be multiplying the correct matrices by each other. Okay. So another thing that we're going to need is the unit matrix, which is simply a matrix of ones on the diagonal. So this is called the diagonal along here, and then we've got 0 everywhere else. And I've written 0 sort of in large, but what this really means is that all of the other elements of the matrix are 0. Okay, and when we multiply a vector, for instance, x1 down to xn, by the unit matrix, all it does is it gives you back the same thing. It does nothing to the vector. Okay, so the thing that I want to focus on for a little bit now is how we can think about these matrices and how we can think about these equations, because I think that in mathematics, representations and being able to move between representations is extremely important. Okay, the more ways that you can think about the same thing, the better. Okay, so I said before that we can write down some system of linear equations, and we can write that as a matrix. So great. So we have sort of two representations. We have the set of equations and we have the matrix. But another way to think about it is that a single linear equation in n variables defines an n-1 dimensional plane. Okay. Now, what do we mean by that? What that means is that, let's say we're in 3 dimensions. We've got x, y, and z. And we write a single linear equation in x, y, and z. What that does is it puts a constraint on, let's say, z. We can actually think about it in terms of a constraint on anything. But let's say we have the equation x plus 2y plus 3z equals 4. Okay, just some random equation. This equation says that if I give you x and y, z is constrained. Okay. Now, what does it mean to have a constraint in 3-dimensional space? Okay, it means that we no longer have the freedom to move anywhere in the 3-dimensional space. We're stuck on a plane in that case. So here we started off in a 3-dimensional space, and we're stuck on a 2-dimensional plane if we have a single equation. Okay, so actually let's look at it in an even simpler context. If we have two unknowns, x1 and x2 in just 2-dimensional space, well, I can write x2 here as minus x1 over 2 plus 3 over 2, and it gives me a line. Okay, this is all pretty basic stuff. Okay, so in this case, it's a single linear equation in 2 variables, which defines a 2 minus 1-dimensional plane, and a 1-dimensional plane, that's just a line. Okay, so we can now think that a single equation corresponds to this plane, or a line in this case, but we can think about it as a hyperplane in generality. So we might be in a 100-dimensional space. We have a single equation in a 100-dimensional space, and it's going to give us a 99-dimensional plane, a hyperplane. Okay, but what happens if we have more than one equation? So in this case, what we've got is 2 equations corresponding to 2 lines in 2 dimensions. And remember that we spoke about before the options that we could have, either no solutions, 1 solution, or an infinite number of solutions. Well, that's what's happening here, that here we have 2 equations in 2 dimensions, but those equations correspond to lines which are parallel, and there are no points in the x1, x2 plane here which satisfy both of the equations. So in this case, there are no solutions. Okay. In this case, again, we have 2 lines corresponding to 2 equations in 2 unknowns, and there is a single point in the space here which satisfies both of the equations. So there is 1 solution to this set of equations. And then here, we might have, for instance, x2 equals 1 plus 1/2 x1, and 2x2 equals 2 plus x1. Well, really, these are the same equations. One is just a constant multiple of the other. And so, in fact, we really only have 1 constraint here. It looks like we have 2 constraints because we have 2 equations, but really one of them is just some constant multiple of the other. And so here we have an infinite number of solutions. Okay, anywhere along this line is a solution to both of these equations. Okay, so what one should be able to think about is this relationship between sets of linear equations, matrices, and the way to represent a set of linear equations by matrices, and the fact that what this is really representing here in terms of these equations are constraints in some space. Okay, they're sets of hyperplanes in some space which may be intersecting in various numbers of dimensions. Okay, So just very quickly for matrix multiplication, here's a couple of quick examples. So if we take a square matrix, which is one where we've got the same number of rows as columns, so this is a 2 by 2 matrix. So here we multiply, we do the dot product of 1, 2 with 3, 2. And so the top entry is 1 by 3 plus 2 by 2. And on the bottom, we've got 3 by 3 plus 4 by 2. So this gives us 3 plus 4, 7, and then 9 plus 8 is 17. Okay. So what have we got here? So we have some matrix multiplication here. We're in 2 dimensions here. 3, 2 corresponds, we can think about that as a point in a 2-dimensional space. Okay, so I can take some 2-dimensional space, let's call it the x1, x2 space, and this here represents some point in the space. So 3, 2, it represents some point here. So matrix multiplication here, when I apply the matrix multiplication to the point 3, 2, it gives me some new point, 7, 17, which is, well, somewhere off here. Okay. So what we see here is that the matrix multiplication has actually performed a transformation on this point in the plane. It's moved it from here up to here. And if I took that same matrix and I multiplied it by some other point in the plane, let's say I took some point over here, it would give me some other point over there. Okay. So matrix multiplication is an operation which takes some vector, and I can think of a vector here as just some point in the plane, and it gives me a new vector, some new point in the plane. So really it's a transformation of points in the plane. If I were to take this one here though, so this top matrix multiplication, so it's a 3 by 2 matrix, 1, 2, 3 on the top, 4, 5, 6 on the second row, and I multiply it by 1, 2, 3, well, it does something a little bit different. So 1, 2, 3 is a point in a 3-dimensional space. Let's just draw that here. So if we have x1, x2, x3, the point 1, 2, 3 is at 1, 2, and then I go up 3. So this would be the point 1, 2, 3. I'll just write it like that. Okay. So what we're doing here, if we multiply the point 1, 2, 3 by this matrix, again, a matrix multiplication, it's actually going to give me a point in 2-dimensional space. Okay, so let's actually just do that quickly. I'm just going to get rid of this here. What's it going to give me? It's going to give me 1, 2, 3 dotted into 1, 2, 3, which is going to be what, 1 plus 4 plus 9, which is going to be 14. And then the second row, I'm going to have to do this quickly in my head, is going to be 4 plus 10 is 14 plus 18 is 32. I think that's right. Okay. So this isn't a transformation in the plane. Okay. This matrix multiplication here is taking a point in 3-dimensional space and somehow turning it into a point in 2-dimensional space. We can think of this as projecting it down to 2-dimensional space, but it's not just a projection, it's some projection with some other transformation. Okay, so we have to be a little bit careful there. So matrix multiplication isn't just transformations in the plane or transformations in 3-dimensional space. It can actually change the dimension in which the point lives. So in this case, we're multiplying a point in 3-dimensional space and it's giving us a point in a 2-dimensional space. Okay, so remember, we can think of functions as mappings from one set to another set. Okay, we're starting here with points in 3 dimensions, and we're ending up with points in 2 dimensions. Okay, so really we should think about this as a mapping. This matrix multiplication is mapping us from R3 to R2. If we had a 2 by 3 matrix, so a matrix which had 2 columns and 3 rows rather than 3 columns, if we had a matrix which had 3 rows and 2 columns rather than 2 rows and 3 columns, that would be a matrix which takes us from R2 into R3. Okay, and of course, if we have some m by n matrix, in general, that's going to take us from an n-dimensional space into an m-dimensional space. Okay. In 2 dimensions, if we just have a 2 by 2 matrix, well, there are various different things that matrix multiplication can do. It can rotate points in the plane, it can reflect about any axis, it can shear, it can project, and it can dilate. And by dilation, we mean scaling, but it can scale differently in different directions. Okay. By shear, it means that we can sort of tilt, take something and we can, what's the best way to think about it? It's not quite a rotation, it's like moving in different directions along different planes. Okay. And then projection is to, for instance, take a point, we take all of these points, projecting these is like shining a light from above, and they end up, for instance, on the axis here, but it might be that they are projected onto some other axis. Okay, it doesn't have to be one of the coordinate axes. Okay, are there any questions about any of this at the moment? Are people relatively comfortable? Can I have a thumbs up if you're feeling comfortable at the moment? Stanley, is that a question? That's a thumbs up.
That's a thumbs up, sir.
Okay, sure, no worries. All good. Brilliant. Okay, and can anybody tell me if there are questions along the way? Very good, thank you, Stanley. Okay, fantastic. So we said that matrix multiplication can take some vector and give us another vector. It's a transformation on a vector, but it can take us from one vector space into some other vector space. It can take us from R3 to R2 or R75 into R1, depends on the dimensions of the matrix. But of course, you can think about what would happen if I went from R3 to R3 to R2. So if I had some operation which took me from R3, maybe to R3, so still in the same space to R2, okay, I can think of this overall as some mapping simply from R3 to R2, okay? It just happens to go through a transformation in R3 first. So all this means is that we can compose matrices together, okay? So if I have some vector and I multiply it by some matrix, I can multiply it by another matrix, okay? And this will give me some vector, okay? But the point is that I can take these two and I can multiply these two together, and this is simply some matrix, okay? So composing matrices together gives me another matrix. In general, if I take an n by k matrix, okay, I've written it in terms of the indices here, A and some matrix B, it's very important that the indices here match the indices here, and I'm going to end up with some new matrix. And the dimensions of the matrix are going to be the same as the dimensions of n and the dimensions of m, okay? So it's really important. So in this particular example, I'm actually multiplying 3 matrices together. And it's important that the dimensions along here, so I'm looking at the middle one, the top row, the dimensions of the top row, well, of all of the rows, match the dimensions of each of the columns here. And similarly, the dimensions of this row, or all of these rows, must match the dimensions of the column of the matrix in the middle. Okay, so getting the structure right, as I said before, is really half the battle. It's very, very important. And if you're coding this up in Python, you're using PyTorch or TensorFlow or NumPy. So NumPy is a very, very useful package. Did you see any coding last week in NumPy?
Yes, we did.
You did? Okay. Oh, fantastic. Okay. So you will have seen then a bit of matrix multiplication, and it's really, really key to get the matrices right. Okay. Very good. So what else do we need to know? So a given matrix may have eigenvectors. Okay. So what does that mean? So we said before that, I'm just going to draw it here. A given matrix will take points in the plane and transform them to some other points in the plane. Okay, I can think of each of these points not as just the coordinates of the point, but as a vector. So it's taking some vector here, and a matrix multiplication is taking it to some other vector there. Okay, so some matrices, not all, but if you take some random matrix, then in general, it will have this property, is that some vectors, when you multiply them by the matrix, they don't rotate at all, they're just scaled. Okay, so we might have some matrix which takes this particular vector here, and it sort of rotates it and it scales it. But maybe if we take some other vector, some vector here, and we multiply it by the same matrix, it's not showing up now, is it? Okay, I'm going to have to stop sharing again. And reshare. Okay, so if we take some other vector, like the vector here, okay, good. Some vector here, and we again just multiply it by the same matrix that we used, which rotated this first red vector, that actually what happens is it doesn't rotate it at all, it just scales it. Okay, that is to say that if we take some matrix and we multiply it by some vector, and I'm just going to use the arrow on top of the V to say that it's a vector, that for some special set of vectors, it gives me the same vector back, but maybe scaled, lambda times V. Okay, and this is called an eigenvector, and this is called an eigenvalue. Okay, and the eigenvalue just tells you what the scaling is. So the eigenvectors of a matrix are simply the directions in the space which aren't rotated by the matrix, but are simply scaled. Okay, so let's say, for instance, if we take a matrix that looks like this, 0, 1, 1, 0. So what does that do? Well, it swaps the x, y coordinates. Let's just check that. So 0, 1, 1, 0 multiplied by some point or some vector x, y. Well, that's going to give me y, x. So in general, if I take some point 3, 2, 5, 7, whatever, it's going to give me 2, 3, 7, 5 as the output. But there's a very special set of vectors, which are vectors of the form AA for any value of A, okay, such that when I multiply it by the vector, by the matrix, it returns the same vector, okay? And of course, that makes sense. So if I think about it, what's this doing? Well, this matrix here is swapping the x and y directions. And sometimes I'm going to call it xy, and sometimes I'm going to call it x1, x2. One important thing in mathematics is that you should be flexible in terms of representations and labelings and these sorts of things. Sometimes xy is going to be the easiest thing to use, sometimes x1, x2, x3. Don't worry about that too much. Okay. So, of course, what this is telling us is that points on here get mapped to points over here. Okay. And a point over here gets mapped to a point over here. But there's some special set of points, which are the points along the line here, where any point along here, and I can think of the point as the vector which is joining the origin to the point, it's going to stay in exactly the same place. Okay. In fact, in this case, the value of lambda is just 1. Okay. In this case, they're not even scaled. They just remain exactly in the same place. Okay, so the eigenvector equation here, the eigenvalues of the system are 1 in that case. Okay, actually, there's another set of vectors which are a minus a. Okay, these, if I multiply by 0, 1, 1, 0, what does this give me? Well, it gives me minus a, which is the same as minus a minus a, okay? So this is another set of eigenvectors, okay? And when we talk about a set of eigenvectors, actually we only need a single vector in the class, okay? So we could choose 1, 1 as the eigenvector within this class, and we can choose 1, minus 1 as the eigenvector within that class, and this class has eigenvalue minus 1, okay? Whereas the other one has eigenvalue 1. So remember, this is the eigenvalue. Okay. Okay, so this is just a summary of what we wrote there, that in general, if we have some matrix M, there may be some set of vectors where the vectors remain the same under matrix multiplication. Okay. So this is generically true with square matrices. Of course, if we start with, for instance, a 2x3 matrix, that's going to take you take a vector in three-dimensional space to a vector in two-dimensional space. So there's no way in that case that the vectors can be the same when you perform the matrix multiplication. But there are still sort of there are still concepts from eigenvectors and eigenvalues that you can take over to non-square matrices, but we're not going to deal with that too much. Okay. So in this case, this is a very similar matrix to the one we saw before. We just had 0, 1, 1, 0. Now we've got 0, 2, 2, 0. And now the eigenvalue for AA, or 1, 1, is 2. Okay, which tells you that if you take the point 1, 1, you multiply it by this matrix 0, 2, 2, 0, the direction of the arrow remains the same, okay, but it's just scaled by a factor of 2. Okay. Something else that we need to know about is the determinant, and the determinant here of a matrix of the form ABCD is simply the A value multiplied by the D minus the B times the C, just this object here. And this tells you something about the scaling, okay? So it tells you something about the way a vector is going to be scaled when you multiply it by this matrix, okay? Sometimes it's written like this, so you just take A, B, C, D, and you put straight lines on either side, okay? We're just talking about notation here. We're not going into details. The one thing which is quite important here is that if we have a matrix and its its determinant is 0, okay, it's going to be what's called non-invertible, okay, which I'm not going to go into the details of that at the moment. Okay. But we do need to know about the inverse of a matrix A, and the inverse of a matrix A is the matrix, and we call it A to the minus 1. This is simply the inverse of A, and this is simply that matrix which, when we multiply it by A, gives us back the unit matrix. Okay, it doesn't always exist. Indeed, if the determinant of the original matrix was 0, then the inverse doesn't exist at all. Okay, so we have to be very careful with that as well. Okay, and really the way to think about the inverse here is, remember, a matrix performs some transformation in the plane. If the matrix exists, if the inverse of the matrix exists, then that means that we can undo the transformation. So, for instance, if we have a projection of points onto a line, that's not invertible because we've lost information. So, if we take points here and we project them down onto the x-axis, okay, we'll end up with points along here. Okay. So if we do that, well, in that case, that's not invertible. The matrix of projections is not invertible, and in fact, the matrix of projections, well, is simply 1, 0, 0, 0, because there's no way to know where this point came from. Okay, we don't know that it came from that particular height. Okay, so that's very important. So some matrices are not invertible, and indeed we have to be very careful when we've got non-square matrices, when we're going from one dimension to another dimension, whether or not they're invertible. Sometimes there will be, they'll have a sort of pseudo-inverse, and sometimes there won't be. Okay, so we've got this relationship here between matrix operations and linear algebra. Okay, and how we see that is that solving systems of linear equations. So let's say we have some system of linear equations here, ax plus by equals c and dx plus ey equals f. We can convert this into a matrix equation, simply like this. So we're going back to what we did at the very beginning. And to solve this, we need to find the inverse matrix of this object here. And I'm not going to go into the details of how to do that. It's not terribly important for what we're interested in, but there's a method for calculating the inverse of matrices if the inverse exists. Okay, we're also going to need to know about the transpose of a matrix. And for the transpose of a matrix, all we're doing is we're swapping the columns for rows and the rows for columns. So for instance, if we take the matrix 1, 2, 3, 4, and we perform the transpose on it, then the row becomes the column becomes the row. So it's basically reflecting the whole thing about the diagonal. So it becomes, rather than 1, 2 along here, it becomes 1, 2 down here, whereas here it was 1, 3 in the column, now it's 1, 3 in the row. Okay. We can also take the transpose of non-square matrices. So 1, 2, 3, 4, 1, 2, 3, 4, sorry, 1, 2, 3 here, 4, 5, 6 here, becomes 1, 2, 3, 4, 5, 6. Okay. The other thing that we're going to need is the definition of an orthogonal matrix. And an orthogonal matrix is a square matrix such that if you take the matrix and you multiply it by its transpose, or you can do it either way around, either A transpose A or AA transpose, then it gives you back the unit matrix. Okay. So what that tells you then is that A transpose, simply swapping the rows for columns, okay, gives you the inverse matrix. Okay. And in fact, what that means is that this is a pure rotation. Okay, so an orthogonal matrix is a pure rotation matrix. And it doesn't scale at all, importantly. This is going to be extremely important. Why is it called an orthogonal matrix? Well, for an orthogonal matrix, all the columns are orthogonal vectors and all the rows are orthogonal vectors. So as an example, as a very, very simple example, if we took 1, 0, 0, 1. Actually, I said there that it's a pure rotation. It can also be a reflection. Okay, so it can also be an inversion. Okay, so if I take the simplest of all matrices, 1, 0, 0, 1. So here, if I dot 1, 0 with 0, 1, okay, that's 1, 0 dot 0, 1. It gives me 0. And this is important that every column and every row, when dotted into any other one, it gives 0. So what that tells us is that this as a vector is orthogonal to this as a vector. And indeed, if we had a 3 by 3 or a 4 by 4 or an n by n, an orthogonal matrix is one such that each of the vectors dotted into each other gives 0. Importantly, in this case, it also means that they have unit length. Okay, so for instance, 2, 0, 0, 2, that would not be because the vector 2, 0 is not a vector of 0 of unit length. It's of length 2 in this case. Okay, very good. Are there any questions at the moment? Again, you're going to have to put the hand up or just turn your microphone on. Because I can't see the chat for some reason. Okay, I'm going to take it that there are no questions at the moment. And this has stopped working again. Hang on. Share. Again. Okay. So why do we as data scientists care about any of this? So, I've been telling you about all these things in linear algebra, different operations that we can perform on matrices. Can everybody see this? Can I have at least one thumbs up? Yeah, thank you very much. Okay. So why do we care about this? Well, it turns out that within data science, matrices show up all over the place. Okay, they're extremely important. And the reason for this is that we can represent data very often as matrices, and many of the operations that we want to perform in terms of machine learning, for instance, can be written as operations in matrices. Okay, in terms of matrices, matrix inverses, matrix multiplications, all of these sorts of things. Once we represent our data and the parameters of our models in terms of matrices, and vectors, then we have all of the tools of linear algebra at our disposal to manipulate, to analyze, to deal with this sort of data. Okay. So as a very simple example, so let's say we had some data, and it was, let's say here, people's height and people's age. Okay, I've given each of them an ID number, but doesn't matter. All we're interested in here is the height and the age, and I can simply represent this as some matrix here. Okay, and I can think about taking this data and I can think about plotting it. So maybe we've got height and age, and this is some set of data like this. And the aim of this may be that we want to take, I haven't actually drawn these points specifically for here, but we can imagine there's going to be some correlation between height and age. And what we might want to be able to do is to take this data and generalize. And that's really what we want to do so much of the time in data science, is perform some generalization. And what I mean by that is to say, okay, I see that there is some trend here. Okay, and I can think about finding some line of best fit. I think you would have seen last week about linear regression. I find some line of best fit, but why do I do this? Well, I do this because it allows me to make predictions. Okay, so now if I have somebody of a particular height, it allows me to make a prediction about their age here. Okay, so I might guess that given somebody's height, I can guess their age based on this data. Okay, and the point is that I can do all of this using matrices. Okay, actually, in this case, this isn't particularly interesting because I have only one set of inputs and one set of outputs. What's more interesting in general is if I have a high dimensional set of inputs. Maybe I've got height, languages somebody speaks, education they have, foot size, whatever, and from that I want to be able to predict age. That's a kind of weird example, but you know, that's an example where you have might have many features. Okay, and features are your inputs, and in that case you have one output. Okay, you have a single output, but of course it may be that you have many inputs and many outputs. Okay, and there we can think about taking some set of inputs and multiplying it by a matrix, such that it gives me some set of outputs, and then I can think about taking inverses of matrices and using that. We'll see that a little bit later on. Okay, very good. What else? Well, maybe we have images, and an image itself can be converted into a set of numbers. So in this case, this is an 8-bit image, which means that the pixel values here, the lightness, darkness is represented by a number from 0 to 255, where here 0 here is the sort of perfectly black number, and 255 is completely bright. Okay, and everything in between. So we have a 116 here, which is sort of gray. And so we can represent a picture like this. If we had a picture which was in color, so what you would have there in general, you could imagine having, for each pixel, you have a red value, a green value, and a blue value. So for each pixel, you're actually going to have 3 numbers associated with it. Okay, so what one very often wants to do with something like this is actually to take this, we can think of this as a matrix, but what's actually very often easier is taking this and turning it into a very long column vector. And the way you do that is you take each of the columns here and you stack them on top of each other. So just very simply, if I had some very small image, let's say a 3x3 image, 1, 2, 3, 3, 2, 1, 2, 1, 3. I could turn this into a very long column vector, which would be, let's say 1, 3, 2. I've just taken this first one, then 2, 2, 2, 1. I've taken the second one, then 3, 1, 3. Okay. So I've taken a matrix and I've just turned it into a vector just by creating one long vector. And it turns out that for many of the applications that we want to do in terms of in terms of neural networks and things like that, what you want to be able to feed into the network is something like this. Okay, is a single long vector rather than putting it in as the image itself in terms of the matrix. Okay. The output in this case, maybe we're going to want to predict where the digits, and if you look up the MNIST dataset, the MNIST dataset is a dataset of many thousands of handwritten digits. Okay. And very often a sort of one of the first problems that you look at in terms of neural networks is classifying the handwritten digits from the MNIST dataset. Okay, it's sort of one of the first problems that you might tackle. And the aim there is you give it a column vector and you want it to be able to predict an 8. You want the outcome to be 8. Or that is to say, what you want it to be able to output is what's the probability of each of the digits? And maybe in this case, it's going to say that if you've trained it well, with 99% probability, it's an 8. Maybe with 0.025% probability, it's a 9. It's just a very badly written 9 or a 6 or a 0, for instance. But you want it to have the highest probability for the digit that you know that it is, because it's in this case, it's a labeled data set. Okay, very good. Okay. Shall we take a 2-minute break here? I think this is actually not a bad time for a break. Are there any questions at the moment? Any questions? I'm just going to stop sharing for a moment. Are people happy with the pace at the moment?
Yes, sir. I know that
Yep.
the pace is great, sir. The pace is great.
Okay, fantastic.
Yeah.
Okay, wonderful, wonderful. Does anybody have any questions about what we've done so far? Maybe actually what would be useful for me is if you can just type in a single digit from 1 to 10, saying where 10 means you knew all of that or already, you've seen it a million times before. 1 means you've never seen any of it at all, and digits in between mean you haven't seen very much of it, or you've seen quite a lot of it. That would be very useful for me to know sort of how familiar you are with it at the moment. So if you can just type into the chat, I can see the chat finally. Okay. And don't be afraid if the answer is 1 or indeed 10. Okay. Okay, very good. Okay. So you should all be able to message me later on as well if you have any questions about this. I'm also very happy to answer any questions. Okay, great. Okay, fantastic. That's good news. Okay. Let's get to Sharon. Okay. Can you all see this again?
Yes, sir.
Okay, great. Okay. So, as I said at the beginning, one of the things that we so often find with very large data sets is that if we try to train our model, okay, be it a neural network or a linear regression or whatever it is, on the data with all of the features, okay, it may be that it's very, very difficult to train because there's lots of information in there which simply isn't useful at all. Okay, we don't know it from the beginning. And one thing that we would like to be able to do is to remove somehow the information which is in there which is not useful, or indeed compress the information in some way. And this may be true for some data set, or it might simply be true for, let's say, an image. Okay, you might have an image And you will all have seen that you could have a JPEG, for instance, and there are different ways to compress a JPEG. Okay, so you take all of the pixel values in some bitmap. Okay, and you could ask the question: is there some way to encode that information in a simpler way? Okay. So now, as a really simple example here, so let's say we had some image which was like this, okay, and everywhere was zeros, apart from this, which was 255, okay, and everywhere else was zeros. Okay. So if I wanted to encode this simply as a bitmap, that is to say, just the pixel values of every single pixel, well, in this case, this would be a 4 by 5. So this would be 20 individual pixels, and each of them is an 8-bit number. Okay, so in fact, all of these are 0, 0, 0, 0, 0, 0, 0. Okay, it's a lot, sort of a lot of encoding there, and this one here is 1, 1, 1, 1, 1, 1, 1. I think that's right, isn't it? 1. Okay. So if I wanted to encode this whole thing, I've got to write down actually a relatively large number of numbers, okay, for what seems to be very little information. Okay. So somehow I could also encode this simply by saying that, well, it's 0 everywhere, and it's 255 at the 1, 2, 3, 4, 8, 9, 10th position, okay, if we count along the rows, okay. So clearly, I could also write this whole thing as at position 10, 255, else 0. Okay. That would seem like a simpler way of encoding the same information. And you could take that and you could go and reproduce the image exactly. Okay. Seems reasonable, right? So what about if instead of this I had, let's say 254 here? Okay, so there's a 255 and there's a 254. Okay, so I could say at position 10 there's 255, at position 10, 11, 12, 13, 14, at position 14 there's 254, else 0. Okay, so I could say at 10, 255, at 14, 254, at let's say else 0. Okay, so that would be a perfect encoding. Okay. But maybe I don't really care about the fact that, well, one of them is 254 and one of them is 255. Both of them are pretty close to being a sort of completely bright pixel. Okay, so maybe instead I could say at 10 and 14, let's just approximate it by 255, else 0. Okay, so we see here that this representation here of the first one, where this is only a single 255, it's a perfect compression. You could take this and you could then recreate the whole image absolutely perfectly. Okay, that's the same here. In this case, you can recreate the image absolutely perfectly, because you're told that at position 10, it's 255, at position 14, it's 254, else it's 0 everywhere else. Okay, and you could go and you could reproduce the picture perfectly. In this case, I've said that at 10 and 14, it's 255, and everywhere else it's 0. Well, I can't reproduce the image perfectly. Okay, I've lost some information there. In fact, this is what's called lossy compression. Okay, which means that I've compressed the image, but I've lost a bit of information. Okay, maybe that's important, maybe it's not important. It depends what you want. Okay, there are many, many different ways to compress the information within an image, and this is called dimensionality reduction. Okay, dimensionality reduction can be used in many different ways, but one of them is compressing the information in an image. Okay, so another use of this thing that we're going to be dealing with for a little while now, the so-called singular value decomposition, is that it allows us to solve matrix equations of the form some matrix times X equals B for non-square matrices. Okay, so I told you before that, for instance, if we had AX equals B, where X and B are of the same dimension, which means that A is a square matrix, well, it's actually relatively easy to find the inverse of A if it exists. Okay, it's not always easy to find the inverse of A if A is not a square matrix. The singular value decomposition is going to be one way to perform to find the inverse of such a matrix. Okay. The singular value decomposition is very similar to a Fourier series. Okay, so in a Fourier series, what do we have? So in a Fourier series, we might have some function, and it might be some complicated function like this. Okay, and I can break this down into a sum, okay, of sines and cosines. So maybe there's one which looks a little bit like this, and then there's one which looks like this, and then maybe there's a bit which looks like this. And if I add all of these together, okay, it gives me that. So this is a Fourier series. A Fourier series is simply saying I take some function, okay, which may be arbitrarily complex, and I can write it down as a sum of sines. Actually, I can write it down just as a set of sines because I can have a phase shift as a set of sines of different amplitudes and different frequencies. Okay, and this is used in all sorts of areas of science. If I take somebody's voice, okay, I can take the signal, the audio signal, and I can break that down into all of the different frequencies and all of the different amplitudes. Okay, and in this case as well, I can say, well, maybe actually if I want to do this really, really sort of accurately, I'm going to need maybe, 1,000 different frequencies. I'm going to have to add them together with all the different amplitudes. And given that, you would be able to perfectly reproduce this function. Okay, but maybe I don't care about, the really, really tiny vibrations within this. So maybe I can actually take, let's say, the first 100 frequencies. The really high frequency stuff I can get rid of. And actually, maybe the really low frequency stuff I'm not interested in either. Okay, if, for instance, I'm taking some audio signal and I want to compress it in such a way that when I play it back, it's going to sound pretty similar to how it sounded before. Well, maybe I don't care about the really high frequency stuff because the human ear can't hear it. And maybe I don't care about the really low frequency stuff because the human ear can't hear it. So here I can take the Fourier series of the piece of music, the audio, whatever it is. I can take all of those frequencies and I can get rid of some of them because for whatever reason, they're not important. Okay? Maybe I want to compress it. Okay, and so I want to be able to save it in, save the information in less space. Maybe it is that I want to just put it into a form where, the human ear can hear it. And then I don't care about the high and low frequency stuff. Okay, does this make sense? Can people type into the chat, again, from 1 to 10, how comfortable they are with the Fourier series? Okay. Okay, perfect. Well, we're not going to be doing any Fourier series. So that was maybe a bit of a moot point. But I want to give you this idea that the singular value decomposition is in many ways very, very much like the Fourier series. But it's not for functions like this, it's for matrices. Okay, so it's going to allow us to take some data in matrix form, and it's going to allow us to perform what's essentially a sort of a series expansion, a series of terms added together, where the terms are going to become less and less important. Okay, we're going to be able to truncate it, and in truncating it, we're able to compress the data, or indeed find the features in the data which are the most important features. Okay, so let's see. So we're going to take some data sets and we're going to call the whole data set, in this case, X. Okay, where let's say we've got a set of people, and for each person, we've got their age, we've got their height, we've got their weight, and maybe some coordinates of their location. Okay, and we can take each of these, and each column here is a single person. So here we have M people, and each of the feature set, the feature set for each person is, in this case, oh, actually, I should just put the K down there. Okay, so each of these XKs is an Rn, but in fact, in this case, N is just 4. It's 4 because there are 4 features here. Okay, so we could take a data set like this, set of information about people. We could take a set of images. So let's say we have 1,000 faces, okay, 1,000 pictures of people. Okay, and each of these pictures is a megapixel, okay, 1,000,000 pixels. Okay, and we have to be a little bit careful here, but let's say that each of the images is again an 8-bit image, which means that each pixel goes from 0 to 255. It's simply a number from 0 to 255. Okay, so we can take all of these pictures of people, and please excuse my drawing skills. Each of these pictures of people. Okay, and I convert each of them into a very long, in fact, 1,000,000-dimensional column vector. Okay, and then I stack them all together to create a 10⁻³ by 10⁻⁶ matrix, where the values in the matrix are between 0 and 255. Okay, I haven't done any compression here. Okay, I haven't removed any information. You could take this matrix, so I'll think about this now as a matrix. Okay, I can take this matrix and I could reproduce all of the faces. Okay, so one thing that we see here, so let's just think about this now, is that in this extremely poor representation of faces, okay, we see that there are a number of different features. Okay, well, everybody here has sort of a round face and 2 eyes. Okay, not everybody has that, but in this case, that's true. And there's some variance here in the smile or the frown. Okay, but you can think that everybody's face is made up to start with of this, and then added onto that maybe a smile or a neutral expression or a frown. Okay, and in some sense, this is a very, very sort of hand-wavy way of putting it. In some sense, the singular value decomposition is sort of going to be like this. It's going to be breaking down faces, in this case, into some base face, and then saying that all of the faces are some base face plus some set of features added onto it. Okay, where each of the features, it's not really going to be sort of smile and frown and that sort of thing. It's going to be more abstract than that. But we can think of this as like the Fourier decomposition. Okay, we can take some set of some audio files. Okay, and we can break each of those audio files down into different sums, different linear compositions of the same set of features, where in that case, those features are sine waves of different frequencies. Okay, so let's say you didn't know about Fourier series, and I just said, I've got this set of functions, audio files, and I want you to find an efficient way of breaking them down. Okay, what you might find is that if you were, if you had the right mindset, you might find that actually adding together sine waves of different frequencies was a really good way to do it. Okay, you might find that adding some other set of orthogonal functions together okay, was a good way to do it. It actually depends on the data. So sometimes the data is going to be best represented by some set of sine waves added together with different frequencies, with different amplitudes. And indeed, for audio files, that's generally going to be the case. Okay. The job of singular value decomposition is going to be saying, I've got some set of data. What is the appropriate orthogonal basis of features that I need to create to add together in different linear combinations to recreate the original data set? Okay. And in doing so, I'm then going to be able to say, well, maybe actually some of these features are not useful. Okay. So just looking at this, it might be that we find that the location here doesn't actually, the location doesn't tell you anything about anything useful at all. Okay. In fact, maybe one way of thinking about this, actually, let's think about it like this. So here we've got age, height, and weight, okay, and location. So maybe the weight of somebody is actually very closely related to their age and their height. Okay, we don't know that. But if we want to find some basis sets, so here we have a four-dimensional space, age, height, weight, and location in some fourth dimension. Okay, and every person in the data set corresponds to some point in that four-dimensional space. Okay, so I can represent the whole thing as points in four-dimensional space. But maybe actually the weight is always some simple relationship between the age and the height. Okay, of course, that's probably not actually true, but maybe there's some relationship between the age and the height and the weight. Okay, and actually we could compress this data set down to just age and height and location, and all the information is in there for us if we wanted to calculate the weight from all of that. Okay, there'd be no point in having a data set, for instance, which was age, 2 times age, and I don't know, height. Okay, so I could give you some data set like this, and if you look through it carefully, you go, hang on a minute, the value in the second row is always equal to 2 times the value in the first row. Let's just get rid of that. Okay. Singular value decomposition essentially is like saying, I start with some 3-dimensional space, and I find that actually I can truncate the sort of series, like the Fourier series. Okay, the little the high frequency perturbations, they're not very important. Okay, that's essentially what we're going to be doing. Okay, so how does this work? So the claim here is that we can take some data set X, and again, that data set, oh no, not working again. Stop share. Okay. So the data set here, X, and remember, this is made up of, let's say, individuals. And each of these are features, and those features may be sort of discrete features like height and weight and age, or they might be the pixel values of the images. Okay, and the claim is that we can write this whole thing as a product of 3 matrices. Okay, a product of, oh, could you see what I was writing before? It says you can only see it now. Could you see as I was writing this? Yes.
No, sir.
Oh, okay. Sorry. Yeah. Please tell me if it looks like I'm writing something, but you can't see what's going on. So what I was saying there was that we've got some matrix X, and that matrix, okay, might be something like a matrix where each of the columns is an individual, And each of the rows is some feature of that individual, where the feature might be something discrete like height and weight and age, or it might be the pixel values in the image, where we've taken our image, which is some two-dimensional image, and we've turned it into a one-dimensional vector. Okay. The claim now is that I can write this as a product of three very special matrices. Okay. Two of them are orthogonal matrices. Okay. U is an orthogonal matrix, V is an orthogonal matrix, and sigma is sort of a diagonal matrix. Okay. Not quite diagonal. We'll see exactly why in a moment. And so the U and V are what are called unitary or orthogonal matrices. In fact, because everything we're going to talk about at the moment is in terms of real valued matrices, so there are no complex numbers here. Unitary and orthogonal we can think of in the same way. Okay. So again, as I said before, the definition of a unitary matrix is that if I take its transpose and I multiply it by the original matrix, then both for U and V, it's going to give me the identity matrix. Okay. Now, U and V aren't necessarily going to live in the same number of dimensions. They're both square matrices, okay, but they're not necessarily in the same number of dimensions. Okay. So just writing this down a little bit more explicitly, here I have my matrix X. So this whole thing on the left here is the matrix X, where each of the columns I'm going to call some X1, X2, etc., Xk. Okay, and there are going to be M of them. So there are M of these X's, which corresponds to like 1,000 people. And each of the Xk lives in some space where N, let's say, is 1,000,000, if each of the images is a megapixel. Okay, are we happy with this? Again, I can't see the chat at the moment, so please turn your mics on and say yes, or put your thumbs up. Yep, happy with this.
Yes.
Okay, cool. Okay, so on the left we have our original matrix X, and the claim here is that we have this matrix here, which are called the left singular vectors. Okay.
Sorry, sir.
Yeah, sure.
Sorry to interrupt you, sir. So I
No,
just
please.
have one question, sir.
Great. Yeah.
And I don't know if it's gonna be stupid or not, but
All good.
do all pictures have like the same pixel numbers, sir?
No, that's an excellent question. So let me just add in another page here. Okay, can you see this? It should be blank.
Yes,
Yeah.
sir.
Yeah. So it depends. So if we have what's called a grayscale image, a grayscale image means that each of the pixel values has a single number associated with it. Okay. If it's an 8-bit image, then each of the pixel values is a number between 0 and 255, where 0 means there's no light, 255 means it's the brightest it can be. Okay, and this is like, it's like a sort of a black and white image, but in fact there's gray in between as well. Okay, so the 8-bit is because we can represent any number from 0 to 255 by an 8-bit binary number. This is 8, yeah. So an 8-bit binary number. So this is an 8-bit image. Okay. If we have a color image, then what we can think of is that we've got kind of 3 images stacked, where this is the red channel, this is the green channel, and this is the blue channel. Okay. And again, each of the numbers here may be, if it's an 8-bit image, again, a number between 0 and 255. So you can think that at position, I don't know, 15, 3, which says go along 15, down 3, okay? We've got some pixel here, and we might have, let's say 140 in the red channel, 25 in the green channel, and 13 in the blue channel, okay? And so it would be represented like that, okay? If we had a 16-bit image, then you have a lot more information. It goes a lot further than 255. Then you have 2 to the 16, basically possible numbers there. rather than 2 to the 8. And so you can have all sorts of images like this. You can also have what are called vectorized images. So there's a whole sort of zoo of possible images you can have, but you can really think that most of the images you would ever want to deal with, the majority of them, will either be a grayscale image like this, or will be an RGB image like this. And in general, when you have an RGB image like this, and you want to feed it into a neural network, you might actually just take the whole thing and you'll end up with a column vector like this, where this is the red channel, this is the green channel, and this is the blue channel. Okay. Does that answer the question?
Yes, sir. Yes.
Yep.
Makes sense.
Great. Very good. Okay. So the claim now is that this matrix X, and we haven't seen why this is important yet, or what the use of this is a matrix called the left singular vectors, where each of these individually, I'm pointing at the U matrix here, each of these vectors, U1, U2, etc., UN, are the left singular vectors. Okay. This matrix here, which we called sigma, up at the top, is made up of sigma 1, sigma 2, all the way down to sigma m, in some m by m submatrix. So the whole matrix is n times m. It's not a square matrix, but the top square part of it is zeros everywhere, apart from sigma 1 down to sigma m, where it's non-zero. Okay, actually, they don't all have to be non-zero, and this one is 0. So just as an example, we might have a set of singular values which are 3, 0, 0, 0, 1, 0, 0, 0, 0.5, 0, 0, 0, 0, 0, 0. Okay, so we see here that we have on the diagonal along here, we have non-zero values. It's zeros everywhere here, zeros everywhere here, and it's 0 everywhere here. So we've got a 3 by 3 diagonal matrix on top of, in this case, 3 by 2 zero matrix. Okay. What's important about this one is that there is an ordering here. Okay. The ordering is such that the value of sigma 1 is greater than the value of sigma 2, greater than or equal to, this is important, is greater than or equal to the value of sigma m is greater than or equal to 0. Okay, so they could, in theory, well, they could, in theory, all be 0. That would be a completely trivial example. But some of them could be 0, and some of them can be very small. And this is really important. Okay, essentially, you can think of the values of your sigmas, be sigma 1 to sigma m, as being related to the Fourier modes. Okay, so when we write down a Fourier series, as I said before, we're writing down a sum of sine waves of different frequencies, and we're adding them together with different amplitudes. Okay, so one might want to take, for instance, the largest amplitude mode, which is sort of the one which gives the most of the feature of your original function, and add on something with a lower amplitude to that, and a lower amplitude again, and a lower amplitude again. Okay, and you might want to cut off all of the values of the sine wave contributions which have amplitude below some amount, because they're adding very, very little to the whole thing. It's going to be the same thing in this case. Okay, so what we actually have here in the case, so let's go to the case where we're talking about faces, where we're adding together faces. Okay, I'm sorry, not adding together faces. We've got a data set of faces of different people. Okay, each of these vectors here is like an eigenface. What we mean by an eigenface is it's just going to be an image, again, turned into a column vector. Each of these columns is going to be orthogonal. Okay, so each one is orthogonal to the next. Okay, which means that, so let's think about this again. So here we've got 1,000 images of people. Each of the images is 1,000,000 pixels So it's a million dimensional column vector. Okay. The left singular vectors themselves are million dimensional. And if we take a million dimensional space, how many orthogonal directions are there? Okay, there are a million. Okay, let's actually think about this a little bit. So again, let's say that we have a megapixel image. Okay, a megapixel image is just an image which has a million pixels. Okay, so maybe it's 10 to the 3 by 10 to the 3. Okay, so our image looks like this, and we turn it into some column which looks like this. Okay, 10 to the 6 long. How can we represent that? We can represent this vector as a single point in a million dimensional space. Okay, so here I'm going to not write a million dimensional space, I'm going to write a 3-dimensional space. Okay, let's just go to a really, really low number of dimensions. Let's say that our images are 3-dimensional images. Okay, that's actually, it's quite strange to have something which is a prime number of pixels, but anyway. All of the possible images we can have correspond to points in this 3-dimensional space. This point here might be the point, let's say 1, 6, 14. Okay, that's an image. Okay, it's a set of pixels. It's a set of brightnesses of pixels. Okay, in the million dimensional case, of course, it's going to be a million dimensional column vector, and it's going to be a set of a million numbers. Okay, every single point in here corresponds to some image, and every image corresponds to some point in this space. Okay, now we can forget about the images and just think about points in this space. Okay, in fact, rather than thinking about the points, I can think of the vectors, which are simply the arrows in a rather hand-wavy way, are the arrows which join the origin to the points. Okay, if I've got a million dimensional space, then I can form a million arrows which are all orthogonal to each other. In 3 dimensions, I can only form 3 arrows which are orthogonal to each other. I could choose the coordinate axes, okay, or I could choose some other set of axes, okay, but I can only ever choose 3. Okay, so for instance, if these are the coordinate axes, let's call it X, Y, and Z, then I could choose some orthonormal basis with an axis here, an axis here, and an axis here. Okay, those are 3 vectors which are orthogonal to each other. They're not the coordinate axes, but that's fine. They're just directions in the space which are orthogonal to each other. If I have a million dimensional space, then I can choose some basis of orthogonal directions. Okay, so what I have here in this case is these directions, okay, each of which there are a million of them. Okay, I've got a set of a million orthogonal directions, and each direction is a million dimensional vector, and it corresponds to some points in a million dimensional space, and therefore corresponds to some image. Okay, now if I took the points in a million dimensional space and I just randomly chose some basis of a million orthogonal vectors, okay, each of those is going to be, well, presumably just some completely random scrambled image, right? What I could do instead is to choose it such that, well, the first one, the sort of the first coordinates in this basis is what I'm going to call an eigenface, and it's going to be the point in the space which is sort of the most important, or the thing, the face which all of the other faces are most similar to. I can think about it like that. Okay, and each of the others is going to be another direction in this million dimensional space, which is also going to be some sort of face. And each of these I can think of like my Fourier modes. Okay. The x's, each of the x's being a single real face, is made up in some linear composition where the right singular vectors tell me what combination of the eigenfaces to add together to give me each of the faces. So V1 transpose here actually says what combination of all of the eigenfaces do I need to add together in order to get the face X1. V2 says what combination of all of the faces do I need to add together in order to get X2. Okay, where when I say add the faces together, what I really mean is the images contained in U1 to UN. Okay, so if I were to find this million-dimensional basis, okay, maybe the first 100 of them look quite a lot like real faces, okay, and the rest of them, because they have to be orthogonal to all the others, well, they don't really look much like faces at all. Okay, the singular values sigma 1 to sigma m tell me the importance of the eigenfaces. Okay, what that really means is that the last eigenface un, sorry, this should actually be what do we got? This is going to go to n. Sorry, is that right? Yes, this is going to go to n. The last eigenface, which is associated with singular value sigma n, there should be an n here, okay, it's probably going to be some very small number, which basically says we need to fill up the orthonormal basis of our million-dimensional space, but this one really isn't important at all. We've started U1 with the most important direction in this space. Okay, this is another way to think about it. Okay, so if I take again my million-dimensional space, and I'm really writing it as 3 dimensions. Okay, over here, each of these points again corresponds to an image, and maybe each of these corresponds to a face of a person. Maybe over here, each of these points corresponds to pictures of houses. Maybe over here, all of these points correspond to pictures of cats. Okay, so what I'm really saying is that most of the information, this U1 is a vector which is saying faces are in this direction. Okay, U2 then says, well, most of the faces from that direction are over here. Okay, then there's some U3, U4, etc., and I'm going to add them together in different combinations to give me all of the different features here. Okay, actually, I could take images of cats, for instance. All of these down here correspond to images of cats. I could add together because, again, the U's here form an orthonormal basis, so I can get to any vector I want, okay, using these. But because these are ordered in a way where they're really directions which are most important for creating pictures of people, to create pictures of cats or houses, maybe U1 wouldn't be the most important, okay? Maybe actually UN would be very important for pictures of cats, even though UN is not very important for creating pictures of people, okay? Are there any questions about this? I know that this is abstract in some sense. We're dealing with matrices and thinking about million-dimensional spaces, or 1,000 by 1 million dimensional spaces. It's a bit strange, but is this making some sense?
Can I just ask a question?
Yeah, please, absolutely.
I think I didn't really get the right singular values. You said the V's. Yeah, I think I didn't get the V's. I got
Okay.
the
Sure.
the
Yep.
mid.
No, that's perfect. Sure. So, okay. So we've got our x's are some set of u's, u2, what have we got? un. We've got our sigmas, sigma n, and then we've got our v's, v1, v2, etc., etc. Okay. I can think of my vector v1 as being some set of numbers. Let's call it 2, 3, -4, 7, etc., etc. And what that really corresponds to, oh, it stopped working again. Hang on a minute. Stop sharing. Share again. Okay. So we've got our vector v, we've just taken the first one here, and this vector v1, which is one of the columns here, okay, is some set of numbers 2, 3, -4, 7, etc., etc., which really says the image of person 1 is 2 times sigma 1 times u1, okay, where u1 is the first eigenface, plus 3 times sigma 2 times u2, which is the second eigenface. Okay. Remember, these are sort of images of people which I can add together in different linear combinations to create each person. Okay. And what the vectors here are saying is, for an individual person, a real person in X, what is the appropriate linear combination of these eigenfaces, okay, that I need to add together to recreate my original X. Okay, does that answer the question?
Yeah, thank you so much. It does answer the question.
Fantastic. Very good. Okay. But the important point here is that the first columns here of the first column of U is the most important column in terms of the faces. I can actually get rid of the really high numbers here. Okay, I actually don't care very much about the UN. Okay, actually, I'm sorry, I was wrong. This is M. Yeah, because there are n. Yeah, so there are. I'll explain why in a moment. There are n rows here, and let me make that a little bit neater. This goes up to sigma m, and this is sigma m here. Okay. What this really tells me is that only m of the columns of U are actually important. Okay, I've only got 1,000 faces. Okay, so actually I could, in theory, just write this down. It wouldn't be an orthogonal matrix, but as the original vector. Okay, so somehow it looks like we've actually done the opposite of what we wanted to do, in the sense that we started off by a 10 to the 3 by 10 to the 6 dimensional vector, dimensional matrix. Okay, what's the dimension of U of U? Okay, so remember, it's an orthogonal basis in a million dimensional vector space. Okay, well, how many dimensions is that? This is 10 to the 6 by 10 to the 6. Okay, well, that seems pretty rubbish. We haven't gone down in the number of dimensions, we've gone up. Okay, this here is 10 to the 3 by 10 to the 6, and this here is 10 to the 3 by 10 to the 3. Okay, so somehow we've done damage. Okay, we wanted to be able to compress our information, but somehow we've actually made things much worse. Okay, we're going to see tomorrow how actually that isn't the case, and I'm actually going to stop fairly soon. I think we've sort of come to a good point here to round things out. But at the moment, it looks like we've gone from a 10 to the 3 by 10 to the 6 dimensional data space of all of our images of 1,000 people, of megapixel images, and somehow we've managed to transform it into information in the form U times sigma times V transpose, which has 10 to the 6 times 10 to the 6 plus 10 to the 3 by 10 to the 3 plus 10 to the 3 by 10 to the 3 parameters. And that's good for nobody. Okay? We've actually created a system which is much, much worse. Tomorrow, we're going to see actually why, for a start, most of the U's are not going to be important at all. Not only are they not going to be important, it's not like we're sort of compressing with a little bit of loss. We can actually get rid of some of the UMs, and it's going to be, we're not going to get rid of any information at all. But then we'll find that we can actually compress this more by looking at the structure of the sigmas and seeing that most likely some of the sigmas are going to be very, very small, and so we'll just we'll set those to 0 as well. Okay, and that's going to be very similar to the example that we were looking at. Where were we? The example we were looking at here, where we said, well, 254 and 255 are basically the same. Okay, we add a little bit of sort of error into our compression, but it's probably all right. Okay, and we're going to do a very, very similar thing for the singular value decomposition, where we're going to get rid of some of the singular values. Okay, the sigma m's, the ones which are very close to 0, we're just going to set to 0, which is going to mean that we're compressing our data a bit in such a way that we're losing some of the features, but not too much, in the same way that with our Fourier series, we can throw away any of the modes, the frequencies, which have really, really low amplitude, and we probably don't care about that too much. Okay, if we wanted to represent an arbitrary function with a Fourier series, in theory, we might need an infinite number of modes. But if we want to be able to compress the data, you want to put it onto a CD, if anybody remembers what a CD is, then you would have to compress, you would have to get rid of some of those high frequency modes, but probably because the way digital music works, you wouldn't actually be able to hear the difference. Okay, so we're going to find that although it looks like we've made a terrible mistake, and we've turned some 10 to the 3 by 10 to the 6 dimensional, or 10 to the 3 by 10 to the 6 bytes of data into 10 to the 6 by 10 to the 6, actually it's going to turn out that we haven't. Okay, we can get rid of a lot of that information in a very clever way, and that's going to be the power of the singular value decomposition. Okay, I think I'm going to stop there and see if there are any questions at this stage, including going right back to the beginning.
Hello, sir.
Yes, hi.
So the M here represents, does the M represent the number of features?
So the M here represents the number of people. So here we've got 1,000 people, okay, and we've got each person has a megapixel image. So the M here is the person. Okay, so X1 is one person, X2 is one person, all the way up to XM is the mth person. N corresponds to the space of images. Okay, so it's a million-dimensional space of images where each position in that million-dimensional space corresponds to some picture. It's probably a random picture, but there will be some region of the space which corresponds to pictures of people. Okay, does that answer the question?
Yes, it does.
Great. So what would be very useful for me is please send me an email. Retta, I don't know if they have my email address. Well, let me just write down my email address. So my email address is john.schock@gmail.com. Okay, so please send me an email if you have any other questions, things that you would like me to go into in more detail about any of this. And I'm very happy to go back and reiterate and explain anything in more detail tomorrow. The sooner you can let me know, though, the better. That would be great. Any other questions? Okay. So tomorrow we're going to continue with this, and we're going to look at how we can get rid of some of these sigmas, and then we're going to look at actually what this looks like when we perform the singular value decomposition, and we think about adding together these eigenfaces. Okay, but we will continue with that tomorrow. Very good. Okay, I'm going to stop sharing. Okay. Anything else for now? Or are people happy with that? Thumbs up, thumbs down?
Very happy, sir.
Awesome, wonderful. That's great. Okay, very good. Similarly, if anybody is in load shedding at the moment and watching this later on, because you weren't able to ask questions during the time here, please do drop me an email. I suppose I should have written that at the beginning. Please do drop me an email, and I'll try to answer the question tomorrow. Okay, very good. Thanks very much, everybody. I will see you all bright and early tomorrow morning.
Thank you. Bye.
Bye. Cheers.